All right, this is 2013 number 5. It's a good one. You shouldn't have any calculations to do in this. It should all kind of be thought, conceptual stuff. So here we go. It's 8 total points. This one I'll try to point them out as we go. Sample C2H4, placed in previous evacuated rigid 2-liter container. It's heated up. It gives you like the silliest graph ever, but shows you that the pressure is increasing as the temperature heats up. And then A says describe 2 reasons that the pressure changes as the temperature increases. Talk about the molecules. So if we're increasing temperature, we are increasing temp, increases speed of particles. Heat them up, speed them up. That causes greater numbers of collisions with the walls of the container. Increasing pressure. That's the first one. Increasing temperature increases speed of molecules. It's along the same lines here. Increasing temperature increases kinetic energy. So the molecules hit the walls with more force. So the 2 things are the increasing in the speed and the increasing of the energy or kinetic energy. Those are the same thing, right? But greater number of collisions with the container walls, and then hitting the container walls with greater forces. Those are the 2 that they were looking for in part A. Describe 2 reasons that the pressure changes as the temperature increases. Good. Then they give you this guy reacts with HCl, produces C2H5Cl, represented below. It gives us a delta H here. That's negative, so we know this is exothermic. It says when HCl is injected in a container, the total pressure increases. That's what we just talked about as we heat it up. Then, as the reaction proceeds at 450, the total pressure decreases. Why does the decrease in total pressure occur in terms of molecular level? Well, what's happening as this reaction occurs is we're going from 2 moles of gas on the reactant side to 1 mole of gas on the product side. So when they're put in there, they are hitting the walls more often and harder, and then all of a sudden they're running into each other more often, and so they are reducing the number of moles of gas in the container. So 5B, there is an eventual decrease in pressure as the reaction proceeds because the product have less moles of gas than the reactants. That's what we're dealing with there. We go from 2 moles of gas to 1 mole of gas. We should see a decrease in pressure as that reaction progresses. That's 5B. 5C. Excuse me. 5C says, it is proposed that the formation of this proceeds via a two-step reaction mechanism. Yay, mechanisms. These are easy enough. The first one is the slow step. It says it's a rate determining step. Second one's the fast one. Write the rate law for the reaction. So we just need the things from the reactant side of the first step to write the rate law. And so our rate law is going to equal baby K. Always starts the same way. Rate equals baby K. Our reactant are C2H4 and HCl. So we're going to have C2H4 and HCl. We only have one of each of those in the first step, and so these are both first order reactants in that case. So you don't have to write ones up there. You could, but I wouldn't. Okay, so it's just like that. That's it on part C. Then part D says identify an intermediate in the reaction mechanism above. So intermediates are something that's produced in a step and then reused in the subsequent step. And so it doesn't even ask you to explain, right? Which is great. So when we look at this thing, C2H5 produced in that step, reused in that step. Chloride ion produced in that step, reused in that one. So either of those would be good. It doesn't say identify all of them. It says identify one of them. And so I wouldn't identify all of them. I would just identify one of them. But those two are both viable. C2H5 positive, or not and, or chloride ions. You pick one. Don't write them both. You write them both, it causes you to make a silly mistake. You write the wrong subscript here for C2H5 or something, and then you lose all credit, right? Don't mix any poop in with the brownies, or it all tastes pretty crappy. Good, just be careful there. Then we got part E. Part E says, using the axes provided, draw a curve that shows the energy changes that occur during the process of the reaction. The curve should illustrate both the proposed two-step mechanism and the enthalpy change for the reaction. All right, enthalpy change, we saw the delta H was negative, which means this guy is going to start higher than it finishes because it's exothermic, so it has to give away heat energy as this thing goes. Good? The two-step mechanism, we have to look back at that mechanism that they gave us and recognize that this being the slow step, the reason it's the slow step is because it has a higher activation energy, and that's the first step. And so we've got two humps on this graph. The first hump has to be higher than the second hump. And so you need two humps there. The first hump has to be higher than the second hump, and it's got to finish lower than it started. I probably could do a better job of drawing that second hump there. If the first step was the fast step and the second step was the slow step, this thing would have looked like this. It would have had a low hump like this, and then it would have had a bigger hump, and then it would have been exothermic, right? So the first step being the slow step, the reason it's slow is because that has a greater activation energy than the second hump there, right? And so that's what makes it slow. Remember, this part of the graph, that's all kinetics. The delta H doesn't change no matter what. It's a state function. But the activation energies, they're determining the rate. Then on part F, on the diagram above, clearly indicate the activation energy for the rate determining step of the reaction. Oops, I did it. You have to indicate that. There's your activation energy for the rate determining step. Good. This one, this made up one over here, the activation energy would be from the start to that hump. That would be the activation energy for the initial one, and then the rate determining step, the activation energy would be greater. And that's it. Point wise, let's see if I can rattle these off really quick. You get a point for the first two in part A, you get a point for B, you get a point for the rate law, you get a point for the intermediate. The drawing is worth 2 points. You get a point for showing that it has a two-step process, so for having two humps, and you get 1 point for showing that the products have less energy than the reactants. And then your last point there is for labeling the activation energy. Those are them.